Hello everybody. In this session we're going to look at Newton's method for solving equations. So we have a xy plane here shown in this diagram here, and we have some function of x. Our goal is to find the point where this equation, where this function crosses the x-axis. That is the solution. That is what we want to find out. One way to do that is by using slopes. As you can see in this example, we start with some initial guess. I call it x0. And at that initial guess, we draw a tangent to the actual curve at that point. So if this x0 meets the curve here, a tangent is drawn, which meets the x-axis at a new point, and which gives us a new value at which we're going to draw another tangent, and then another tangent, until we reach the point where the tangent actually meets the solution, meets the point where the curve crosses the x-axis. So the procedure is just drawing a sequence of tangents. Why does this method really work? Imagine if we had a straight line, okay? And we want to find a solution, means we want to find this point x, I labeled it as x2. So let's say I start anywhere, and if I start anywhere and I get this point on the actual curve, at which point, since it's a straight line, if I draw a tangent, that tangent will go right to the point which is the actual solution. So no matter where I start, I will end up this at x2 in just one step. And the same concept is applied in case of any function. So here's a one-shot method. Now let's assume a problem here. Is this guy standing here, and this guy is throwing the ball up in the air. So the question arises, if the ball is going up to a certain height, we want to find the value of time at which the ball will be at some point. Let's consider a scenario where the ball goes through different points in space. Let's say it starts at here, time t equal to 0, and its height at that point is also 0. It starts from the hand of the person. Let's call that at time t0, height is 0. And let's say we measured that at 1 second it was at height 1 foot, and at 2 seconds the height was at 4 feet, as shown by this yellow dot. So the problem that we are trying to answer here is, what is the time at which height is exactly 2 feet from the hands of this person? Now, before we solve this example, let's say height at different times is given by the equation h equals t squared. Now, this may be a different equation, but let's assume this is the equation that provides the height at different points of time. So algebraically speaking, our problem becomes, if height is given by h equals to t squared, find the time when height is equal to exactly 2. In other words, if we express it in a simpler way, it says t squared being the height, has to equal 2 at certain time. T squared equal to 2, solve that equation, or at what time is t squared equal to 2? So what's given here is the graph of t squared minus 2. It's a well-known quadratic curve here. Now, let's take a look at the quadratic curve t squared minus 2 drawn here. The dotted area here corresponds to negative time, which will not make any sense in our problem. So we're just not going to talk about it. But we're going to look at this positive half of the curve, which starts at time t equal to 0 and goes on upwards from there. Now, the way this problem is phrased, initially we had this person throwing the ball up. And we threw the ball up at time t equal to 0, and we want to find out what's the maximum height, or when does this ball reach 2 feet. Now, the way we change this problem in this, the way the equation is written, it means we're throwing the ball at time t equal to 0 from a height of -2 feet. because when t equal to 0, h is equal to -2. So we're really changing this problem. If I throw this from -2, when will this ball reach 2 feet becomes now, when will this ball reach 0 feet? But we have done really a change of translation of the scale. We have moved our at time t equal to 0, initial height equal to 0, we have made it at initial height equal to -2. Now, why would I do that? Because if I look at this graph, we are interested in finding out the solution to this graph. Means, when does this cross this t-axis, which corresponds to this big cross that I'm drawing here. So we want to find out the value of t corresponding to this point. Now, assuming I start at t0, this is my t0, I'm really interested in finding out the point where the curve crosses the x-axis. So our process, as we indicated before, is start at any point, draw a tangent, find a new point, draw another tangent until you hit the actual point. So at time t equal to 0, we draw this tangent, and that tangent, if we know this function h of t, we can easily calculate the value of the tangent at time t equal to 0, which is h prime of t0. And h prime of t0, which is the slope of this red line, is equal to rise over run of that red line. Rise over run, rise, this part here is h of t0, and run being this part, t0 minus t1, that's our run. So this is rise, and this is run. And when we divide them, we get h prime of t0, which is the derivative. And if we solve this equation, if we can write this equation as t0 minus t1 equals h at t0 divided by h prime of t0. So we can just simply write it like that. Here we are expressing that same equation in a little bit different form, in which we start with initial guess and we get a new guess. The reason I wrote it in this equation, because everything on the right hand side of the equation, initial time that we start at, the slope at that time, which is this denominator, and the numerator means the value of the curve at that time. That's also known. So everything is known, so that tells me the new value of time t1. Now if we continue that way, just like our initial choice of time t0 and the slope and the height at time t0 produced as a new estimate for the time, in the same way, if we generalize any word, I call it the initial value, t0 becomes tn minus 1, where n is some value. N could be 8, 10, 12, depends on at what iteration I'm looking at. That will produce a new time. So this formula essentially here is generalized by this equation. Now here's the problem that we started with. The height at different times is given by t squared minus 2, and we want to find out when is that equal to 0. And this second equation here is the formula that is the Newton's method, and in it we need to know what the value of h and h prime, the function and its derivative. The equation and its derivative is at different points. So if we take the original equation, h of t, and find its derivative, which is 2t, and then we're done. So we basically have to use all these terms, all these equations. Let's say we start with n equal to 1. When n is 1, then let's say that our initial choice, where I start on that curve. Remember, this was the curve that let's say initially I started at time t equal to 2. That's what this initial choice is. At the height of that curve at that point, remember it was t squared minus 2. So if we plug that t squared minus 2, it becomes 2, and the derivative of this function at that point is 2t, which simply came out to 4. So if I know all these three values, these are the three values I need to know, 1, 2, and 3. I plug them in and I get an estimate, and the estimate tells me when is this time t1 tells me if we drew a tangent to this curve at this point 2, when will that cut the x-axis? So it will cut the x-axis at 1.5. In this calculation, which you can spend some time on, we repeated the same process. Now instead of using t equal to 2 as the initial time, I used the time I got in the first iteration. There was 1.5, which is simply 3 over 2. We use that time. So we found the height at that time, which is 1/4. We found the derivative at that point, and the derivative was 3, and we plugged all of those in, and we got a new estimate where the derivative, where the slope will cut the x-axis, which is at 1.416. In this calculation here, we started with the previous estimate of time. We find the height at that time, as well as we find the slope at that time. So we know the time that we got previously, the height at that time, and the slope at that time, and plugging all of those into our formula, we come with a better estimate for our time. As you can see, it's even closer to our actual value. Our goal was to solve t squared minus 2 equal to 0, which means if we solve it analytically, which is t squared equal to 2, or t equal to root of 2. If you do this on your calculator and find out how much is the square root of 2, you will come up with about 1.414. I'm going to write just up to 3 digits. And what we just found out in our calculation, on our third iteration, our value was indeed 1.414. So Newton's method really helps you in a quick and easy way how to find these roots. In actual case, it won't be a one-shot method. You will start with some initial guess, get a better estimate, as you can see. Now, there are some cases or some conditions when this method will not work, but we're essentially looking at the simple functions, in which case this method works most of the time. This method of drawing these tangents and finding the solution is called Newton's method.